This video is all about the electron. Electron is outside the nucleus. This is where the chemistry happens at the electron level and an introductory level chemistry class. So we're going to focus on the location of these electrons. They're moving around the nucleus at around 2,200 kilometers per second. So these electrons are moving all over the nucleus. That's all around the nucleus, all outside the nucleus. Remember, the nucleus we're not going to mess with here. So this gets into quantum mechanics, really introductory level. So think of these, each one of these as a cloud of where these could possibly be located at, right? So we have our S block, our P block, our D block, and our F block. We'll talk more about these later. Think of these as clouds where certain electrons are found hovering around. So they are not like in a constant orbit like the Earth around the sun. These are like moving and these just certain clouds is where they can be precisely located with some very complicated math we're not going to get into, okay? So these are the different shapes of the clouds, roughly. F's are crazy, so we're not going to mess with F's. Why? Because F's are found down here on the periodic table, and these are typically man-made. I could be wrong on that, but like we're not going to mess with that, so FF's on for us, okay? So this is another representation of what it looks like. So this is the S block, a sphere. This is the P block, which is a dumbbell, right? And this is the D block. So notice how the purple ones are in different orientations, right? And so this is the D block. So just notice those are where those electrons can be located at, all right? So what students did yesterday was they took a periodic table that didn't have color on it, and they labeled these things. Notice that the blue is the S blocks, the sphere, the P blocks are over here, right? And then the F blocks are down here. We're not going to worry about the F blocks. Okay, they're down here on the bottom. Okay, we're not going to worry about those. But notice that we're going to talk about this in a second. All right, so the students did this and labeled it. And so you'll have the support. And this is how you do this. So on this example here, there's some facts you got to know. So if you want to pause the video right now and write all this stuff down, this is some pretty important information. So it's only 2 electrons for each line. So what that means is if I have helium, which is an atomic number of 2, 1 electron, 2 electrons. So I'm done. So that the orbital notation for this is 1s2. So I'll do that again in a second. So again, if you need these, you need to know there can only fit on each one of these lines 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. Okay, this will really help. And you go from bottom up. Okay, so we're going from low energy to higher energy. And the max for each one are 2 for the S block, 6 for the P block, and 10 for the D block. So again, this example, helium, 2 on the atomic number is 2, which means that's 2 protons. But in a balanced atom, the number of protons is equal to the number of electrons. So when you look at a periodic table, the number of protons will be equal to the number of electrons. So I know that helium has 2 electrons, right? So doing the notation for this to find out where these are located, these electrons, I know they're in a sphere right next to just outside the nucleus. So it's 1s2. So if I wanted to draw this, it'd simply be 1s2. This is in the S block, so it'd be like a sphere, and these 2 electrons are there. Now, what these arrows mean, that's the spin. This is magnetic spin, right? So that means one's going clockwise, one's going counterclockwise, because the electrons are negatively charged. Negatively charged things want to get away from each other. So that is why they would do that. So if I had, let's do another example. Let's do carbon, since we're carbon-based life forms here on Earth. So now we're doing carbon. So carbon has 6 protons, which means it's in a balanced atom, like they all are on the periodic table, they're assumed to be balanced. It's going to have 6 electrons. So I need to get 6 electrons, and I'm going to use my Aufbau principle. You don't have to know the name of that dude. So I need 6 electrons total. So what I like to do is to write down 6 electrons. That's where I'm going. So now these are full, 1, 2. Remember, those are electrons. So now I have 2 electrons. Now I have 4 electrons. 5, 6. So now the reason I didn't fill them up first, because these electrons are negatively charged. They want as much space from each other as possible. Okay, so this is how we write that. I think that's called Hund's rule, if I remember correctly. Could be wrong on that. You don't have to know the name. So now I know I can double check. 1, 2, 3, 4, 5, 6. I have 6 electrons. So my electron configuration for this is 1s2, 2s2, 2p, 1, 2. So this is my electron configuration. So if I want to write it up and tidy it up here, just put them all together. 1s2, 2s2, 2p2. So this is my electron notation for this. So this tells me exactly what the electron clouds are going to look like. I'll explain that in a second. But let me show you where the valence electrons are on this, because I think that's important, because that's where the chemistry happens. These are my energy levels, the same energy level. So those are 2. So the total number of valence electrons for carbon is 4. Okay, so that's my valence electron number. So if I want to know how many valence electrons I had, it's just 2 plus 2 up top here. These two, let me do this again, sorry. 2 plus 2 is going to give me, from these 2 numbers right here, it's going to give me the number of valence electrons. The ones in the outer shell is going to be 4 valence electrons, okay? So this is the scientific notation. I mean, scientific, goodness sakes. This is the electron configuration up here, right? And then the valence electron, which I think is important to know. We'll talk about why we're carbon-based life forms, because of those 4 valence electrons to form all kinds of covalent bonds we'll talk about later. So this is like the representation of how you would do that. So I will show you the scientific, let's draw this real quick. Okay, so I have 1s2. So what I'm going to do is I'm going to write in the middle, really tiny, real tiny, is I'm going to write, it has, even though these protons are and neutrons, 6 neutrons, that's going to be my nucleus, okay? So I haven't even drawn the electron clouds yet. That's probably too small. That's right. So then I have 1 sphere here. I'm going to make this green. This first energy level is going to be green, and there's going to be 2 electrons somewhere in that cloud. Who knows where they're at? Then my next energy level is another S. It's the next energy level, so it's going to be a 2. So I'm going to draw another sphere here, right? And I'm going to put an electron maybe here, an electron here. So there's 2 as well. So in the next one, oh, that's a bad E. My next one is a P. So refer back to your, I'm going to make this one puke yellow. So now I got a dumbbell. So I'm not the best drawer on this. So I'm going to do a cloud here, kind of going up like this, and then a cloud here going down like that. And then I'm going to put 1 electron here, 1 electron here. Okay, so this would be the orientation. This is not the best, but like I have my dumbbell shape, I have my 2 spheres, and I have all my electrons accounted for in that. Now, one last thing. So I'm going to do one more. I'm going to show you noble gas notation for a shortcut. So sulfur is 16 protons on the periodic table, which means it has 16 electrons in a balanced atom. So I've already done it. I filled it up. So I have 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now if I wanted to write that, so it looks like this. So if you add up all these numbers, 2 plus 2 plus 6 plus 2 plus 4, that's going to equal 16. You can check your work. I don't want to write all that. So I can look back at my periodic table and notice that sulfur's right here. The closest noble gas is neon. So I could do neon and delete the rest of that. I'll explain that in a second. So neon, so if I did neon, it is, so if you did this with neon right here, you would notice that it equals 1s2, 2s2, 2p6, right? So that's all of this right here. So instead of writing all of that, right, instead of writing all of that, I could do this. So this is the noble gas notation in this, right? So notice I have my highest energy level and my valence electrons are 6, right? And so neon, so it's neon, that this cancels out all this stuff right here. It's just taking the place of it, right? It's just substituting. So hopefully that makes sense. Quantum numbers, electron configuration, real fast.
Go, hit it.
Oh no, are you serious?
No way.
Are you serious?